about the same thing. Where do I get the answers to these wikis, or where do I put them? So let me remind you just one more time. When you start a wiki, there can be two things going on. One could be there is nothing in there is no answer. And the other thing that could happen is that there is an answer already, but not checked by me. So what you do is you try to answer these assignments in the wiki. If you feel that your answer is better than the one that's in there, or there is no answer in there, put your answer in there. If you feel that it's now complete, the whole wiki as it is, let me know, preferably through a discussion forum, so that everybody can see that I now also know. Then I will look at the wiki. If it's indeed complete, I'll look it up, and you'll have the answer that should be correct. And so there's nothing like submitting in a separate place and that I count how many submissions we have or something. I got all kinds of weird suggestions as to what would happen there. There's only one place where they are, one place where there is an answer. Don't be too shy in getting rid of an answer of somebody else. In the end, you want to have an appropriate or even the best answer there. So that's the way in which it goes. And something else that is important that I noticed myself, check your Canvas settings if you haven't done so yet. I'm not even sure if these settings are particular to the course or to the whole management system. For instance, I found out that in the beginning my settings were such that I got a notification of all your stuff that you've put there on Sunday evenings, so once a week, which is not ideal. So I changed that to, as soon as you post, I get it. And it might be that in your settings you could also find that you get reminders only once a week or perhaps even once a month or so. So check if that works for you, and then you should be getting all the assignments and notifications and who knows what that is online. Okay, so here we go. We went through Stata already and Canvas, we know that. It's all about relating different kinds of variables. That's what we're about to do. The last time I talked about the general logic of hypothesis testing, because we're going to do that lots and lots of times, and we have to know how it works. And now we're going to start with the first one, comparing two categorical variables. That's the shortest one. And the second one that I'll be able to complete, I think, halfway through or so, is comparing a categorical variable with two categories. So boy, girl, or yes, no, with an interval variable. So that's what we're up to. First, categorical by categorical. See how that goes. For that, we, in the end, need to be able to do two kinds of tests. One is called a chi-square test, and the other is called a Fisher's exact test. And basically, these are the only two that we need. In fact, in Stata, it's really easy. So in the end, what you should be able to do is only this. This is what it looks like. First, you have two variables, x and y, and x and y are each categorical. Doesn't matter how many categories they have. What you want to do is make sure that you create a crosstab and look at the table. You do that through tab XY. Then you check all the cell counts. One cell will contain the frequency of the number of cases that you have. So if you have, let's say, an X variable with 5 categories and a Y variable also with 5 categories, then in cell number 1, 1, you'll see how the number there, how many cases are in that cell. You check if these are all at least 5. This is the standard rule of thumb. In fact, there are a couple more rules of thumb in the book, but that's usually what we go by. If that works out, so we have indeed at least 5, then we do tab xy, chi-squared. And if we don't have that, then we do something else that's called Fisher's exact, and that you do through tab xy, exact. That will give you output. The output, once again, has a number in there, an actual test of the thing that we're testing here. And what we're testing here is that, this is the H0, more on this in a minute. All columns are distributed in an equal way, namely according to the marginal. That's the thing that we're testing. Sounds complicated, but actually it's not so bad. Then you get a value that is either above or below 0.05, and depending on what you get there, you either reject or you support that H0. So that's basically the thing that you need to do. It takes a longer while to explain why this is what you need to do and what is exactly happening behind the scenes, but this is basically it. Okay, I need a bit of a run-up there. First, a little bit of statistics. This I had on the slide deck before. This is the normal distribution, where we actually have a formula there that goes with the normal distribution, and if you look closely, you even see here that this is not exactly the graph here that belongs to that one, because here you see a mu in there, that's actually the sigma squared, and that is how wide this distance is, here from 0 to 1, but in principle that could be any number. Okay, so that we went through already. We know the formula, so if you want to calculate on this stuff, that's, well, may not be easy, but at least it's possible. You have an exact formula and you can try to work with it. A couple of rules that are handy to know. First, if you have this, a variable x, that is this tilde over there is meant to suggest is distributed as a normal distribution with a mean mu and a variance sigma squared. So the middle is at mu, and sigma squared says something about how wide it is. Then if I create a new variable where I subtract that mu first, and then divide by that sigma, then I get something that is normal with a mean of 0 and a standard deviation of 1. So if need be, if I have something that has a normal distribution, doesn't matter where exactly it is or how wide it is, as long as the shape is normal and follows that formula, I can create a new variable from that is actually 0, 1 distributed. That's one calculation rule. Anything that has a normal distribution can be made standard normal if you want to. And the other one is if I have two variables, an x1 that is mu1 and sigma 1 squared distributed, and an x2, same thing, and I create a new one as the sum of the one that I had, then, well, the first part is relatively easy to see. The new midpoint of that normal distribution is at mu1 plus mu2. You simply add the two humps together, and the variance, so how wide the thing is simply the sum of these squared numbers that we had in the beginning. So if you sum up two normally distributed variables, you get something else that is, again, normal. Perhaps not so easy to see if you think about, okay, if I have something that looks like this, and I add it to something that looks like that is perhaps way smaller, well, if you add that, then again you get something that has a shape like this. Not that intuitive, I guess. If you want to go through the proofs, these are not very easy. On the Wikipedia page that I referenced to here, you see a couple of examples of proofs, or quite a few, and the three that are there, all are not so nice. If you want to do this, you need some serious calculus, for instance, or some other stuff that you need to really know well. But in any case, the formulas themselves are relatively easy. So we can calculate not only with a single normal distribution, but also add them up and create different ones. Okay. Now, a new statistic that we create based on that normal distribution. In fact, when I gave a slide at some point with a long list of theoretical distributions, this one was also in there. It's called a chi-square distribution. What is that? A chi-square distribution of degree k. That's the sum of k squared independent standard normal variables. Okay, let's do that slowly. So, if x is a draw from a standard normal distribution, that n01 that we saw on the previous slide, then I can also create, instead of x itself, x squared, that also has a distribution. I have the formula for standard normal, so I can square that and get something that has a different distribution, and that thing is then called chi-squared with degree 1, where the 1 is representing the fact that we have only one variable in there. You can do the same thing. Now for two variables, if A is from a normal distribution, I draw from that normal distribution, I square that number. B is also from a normal distribution, I draw from that normal distribution, I square it, and now I add them up. Now it's again a chi-square distribution, but now of degree 2. So that degree says something about how many different squared normal distributions I add up. But first thing to see here is, well, obviously that you have here only positive numbers. You can't have anything else. And you also see that as the k goes up, so the more of these different numbers you add up, the more, let's say, the bulk of the data points is moving towards the right. So it starts with these two, and then where you have a hump sort of on the left, more to the right, more to the right, more to the right. And the more you add them up, the more that thing is moving towards the right. Okay, and have that separately here as well. Okay, so in principle you could simply think, yeah, nice to know, I will need that in a minute. But in principle it's simply using the formula that I have from the standard normal distribution and then doing something with it. And at this point it's not obvious at all why we would actually need this, but in a minute I hope it will be, or at least more so. Okay, that is the statistics background that we need. Now on to two categorical variables from our own data. Here I'm using the actual data that I got from, I think, a year ago. So these are not the cell counts or the frequencies that we have in our data. But we could do it in the same way in our data. Here we have male-female on top. So 63% in this case is male and the rest is female. And I asked, how do you go to TUE by on foot, by bike, by bus, by train, or by private transport? And you get a certain distribution. So indeed, these are two variables here, x and y. Both of them are categorical. And now I'm on my way to try to come up with a chi-square test. So first, let's see what in the end we want to be able to accomplish. Here you see that command that I started about in the beginning. Tab female is one variable. Variable to TUE, that's the other one. And well, you can forget the row for a minute. Then you get the chi-squared behind it. And indeed, in the end, you get a number there. In this case, 0.122. That says something about whether or not H0 has been supported or has been rejected. Yeah, let's see. One thing that you figure out if you improve these kind of things over the years is that if you do it like this, now you see how you travel to TUE most of the time, and then you don't see anything anymore. And the only thing you see is 1, 2, 3, 4, 5, and you have to cross-reference with the survey PDF to see what 1, 2, 3, 4, and 5 are. So usually it's a wise idea to put in the label something like this, where the numbers actually are already showing exactly what it is. But this is what we're trying to figure out. What is that? And I have the same crosstab actually here. Let's see, I have to peek there, yeah. This is the same table as on the previous slide. The only thing that I left out here are the cell counts. And the thing that I leave standing over there are the numbers on the edges, and another word for that are the marginals. Even in Dutch that's a word, marginale. So in this case we have 72 males and 36 females, and well, we're trying to figure out if there is a difference across these different columns from left to right compared to this difference over there. So if these two, being male-female, and which mode of transportation you choose, would not be related, and if we know that there are 70% males and 30% females, well, then we would expect, if none of that makes a difference, that we would get that 70-30% here as well, and 70-30% there as well, and there, and there, and there. That would mean it doesn't matter if we somehow partial out the different ways of transportation to TUE, you get that division 70-30 all the time. Now what would that mean? That would mean that if I have this table, you have here the same table again, now in red, I have the numbers there that I would, oh it's not 70-30, it's actually 2/3 versus 1/3. In red you see the numbers that I would expect if this would be exactly right. So I get 2/3 versus 1/3 in each and every one of these columns. So that's a 2 here and a 1 there, a 16 here and an 8 there, a 2.7 here and a 1.3 there. This of course can never happen because there has to be an integer in there. You can have 3 cases there or 2, but not 2.7. 49.3 versus 24.7, and again 2 versus 1. So this is what I would expect if they are totally independent and everything works out just perfectly. Okay, so now we see a little bit more intuitively what that H0 is. H0 is, well, we expect no differences in the sense that we expect the red numbers over there. Across all the columns, that distribution should be the same. Okay, now we have in gray the actual numbers that we have. So the next thing we need to try to figure out is we should compare the gray numbers that we have here with the red ones that we expect if there are no relations between the two. Well, there are many ways in which to do it, but the smart way to do it, and in the end we'll find out why it's so smart, is doing something like this. We compare the cell counts one by one in the following way. All the same, all the same, the two top tables, you see 3 minus 2 squared over 2. That is that difference here between the 3, the gray 3 over there, and the 2 over there. That difference I square to make sure that I do not add up a -1 and a +1 to conclude erroneously that there is no difference anymore. So I square this difference, and I take into account that I had 2 here as a measure for comparison. Would make a large difference if I had 100 here and then I'm missing only 1 versus I had 2 here and I'm missing only 1. So I take that into account. I do the same thing for each and every one of these cell counts. 45 there, 49.3. I subtract the 2, I square it, and I divide by the 49.3 as a reference point, so to speak. I do that all the way through to 3 minus 2.7, and I would put the other way here, but it wouldn't fit on the line. The 1 minus the 2 squared divided by 1, and then in the end we add that all up and we get a number, 7.27. Now, forget for a minute exactly how this is done, but in any case you can see here, the bigger the differences are, the bigger that number on the right is going to be. So, in a way we are in the same situation where we were with the coin flips. There we were also trying to do something of the same kind. We had 1,000 coin flips, and we know, yeah, we're expecting 500, and we're trying to figure out where the number is, 525, 600, 700, where it starts to be weird. And here, this is actually the same thing. So that's 7.27. It would be nice if you could say something about, is that a high number? Should we expect this, or shouldn't we? And that's exactly what we're going to do here. And what is going to help us here is that this thing over there, that sum of square differences, about that we know that this is approximately chi-squared distributed with 4 degrees of freedom. Okay, that is not something I want to go into in detail exactly how. You can see it coming sort of, that these squares are squares of standard normals in the long run through the central limit theorem. So, you know, forget why exactly this is the case, but again, this is a known distribution, and the only thing that is not helping us very much is that it is approximately distributed as something like this. So we have something to go on, but it need not be good enough. Okay, yeah, and just to remind you of that coin flip example, this is exactly the same thing. Coin flips, we have a distribution that we know, and we're trying to find the edge. Where does it start to be weird? Same thing here for the crosstabs. Yeah, here we have it. Okay, so let's see. Yeah, obviously, you can see here, yes?
Yeah. Why was it now that there were 6 restrictions?
6 restrictions?
Yeah, it's 4 degrees of freedom, and also 10 cells, and 6 restrictions. So that's why there's 4 degrees of freedom.
Yeah, the degrees of freedom here come from the fact, I think I even have a slide about that later on, but if you look at the differences here, for instance, going through this column, here you have a difference, and if you've calculated this number, then the other one is obvious, because that's what is left from the 3. So I have this one, but not that one. And that goes for all the columns over there, so all these I don't use. And at the end, same thing, I have this one, but in principle this is completely determined by that 72 over there, because I have to add up to 72, and that costs me another degree of freedom. So the degree of freedom comes from the fact that you know, this edge here is completely determined by the numbers over there. This is where the 4 is coming from. Okay, so let's see, in Stata, what does that do? We have, and here I have the original table that I had a couple of slides ago. Here I have that same table. Now I added a little bit, something over there. It's called X for expectation. So the numbers that I put in red, you can actually get them from Stata as well if you want. There's no need to necessarily, because Stata will do the math for you. But in any case, here you do see the expected numbers over there, 2.0, 1.0, 49.3, 24.7, and so on. You also see that 7.27 in the end, that the sum of square differences. So Stata is doing all this behind the scenes, and you get, using that we know the chi-square distribution with 4 degrees of freedom, you get a probability in the end. And what is that again? That is the probability that if H0 would be true, that we get data that we have, or data that is even further away from H0. And that here is 0.12 above 5%. So this means H0 is supported, or stated differently, H0 is not rejected. Okay, so apparently here, in this case, there is no reason to really believe that there is dependence between being boy or girl versus what kind of mode of transportation that you take to TUE. Any questions about this part? You do it, you remember what H0 is, and you remember what the crucial border there is, and that below 0.05 means H0 rejected. Let's see, we could do something else here as well. You could, for instance, look at these tables and see that the first and the last column, and the third in fact, all three, don't have so many cases in there. So there are a couple of people actually who come on foot, and also a couple who come by bus, and a couple by car or motorcycle, but that's just only a handful. So if you really want to make an actual comparison, perhaps we should restrict the comparison to only these two columns, that one over there and that one over there. And that's easily possible through the same syntax by adding an if command behind the tag. All this is the same thing. Tag female travel to TUE row chi-squared, and then you add if travel to TUE equal to 2, where we once again need the double equal sign for in value equal to. This is an or you have over there, and then travel to TUE double equal 4, and then you only get the two columns, let's see, bike versus train. Now you see that the three columns that we had before have disappeared from the actual table. And in fact, now, running exactly the same test, you do get a value over there that is, well, it's only slightly, but it is below 0.05. So here we do see differences between boys and girls with respect to what kind of mode of transportation they use. In this case, we find H0 is rejected, contrary to what we had before. Yeah, and in blue, just so you wondered, you might think that that whole exercise that I did, where I went through it column by column, does it make a difference if I interchange the columns and the rows? And the answer is no. So you could, if you would have a 10 by 10 table, and you square these differences either row by row or column by column, none of that makes any difference. So luckily, if you type tab XY or tab YX, that won't change a thing with respect to this number that you get over there. Okay, so that is the, let's say, the easy part. The only thing you have to remember is the tab command and the chi-square, and the answer will come rolling out. However, there is a slight issue here, and that is the following. Well, we needed that we know what the chi-square distribution is with 4 degrees of freedom, but it's an approximation. So we have to think about when that approximation is bad, and when it is, let's say, good enough. And there are, in the book, a couple of rules of thumb when this is actually the case, but the standard rule is, okay, if we have a frequency count of 5 or less, then for that cell at least, that approximation is not very good, and we should better do something else. So actually what I did before, I have to peek if I have that here, yeah. This was the original table that we had before. See, you have 3 and zeros, 3 and 1, 1 and 2s. In fact, that is actually not really good enough to run a chi-squared analysis on, and you should do something else. And then it starts to get a little bit more complicated. Okay, so if that is not working, we need something else, and either a better approximation, but that we don't have, or some other way to calculate this, some other way to figure out if the actual data that we have is close enough to what we would expect theoretically under H0. Yeah, this we had already. Okay, and this is what it's called, Fisher's exact test. And it's not so easy to grasp, and also not so easy to calculate, by the way. We'll run into trouble pretty soon for larger data sets. But let's see how it goes. In this example, just because it's easier to explain, I restricted myself to only columns 2 and 4, simply to make the table a bit smaller. But in principle, this can work for tables of any size. Okay, so what are we trying to achieve here? The idea is as follows. Let's suppose again that we have no numbers in here yet, but are only thinking about, okay, which kinds of distributions of numbers could we have so that they add up to these marginals over there. And the idea would be, well, there are perhaps many ways in which we could have frequency counts in these 4 cells in such a way that they add up to these marginals. And we have to simply check whether or not the one that we have is a weird one in that set of cases that we could have. So one example would be, let's say, erase all these and we start here with a 0. That would work. The 0 there would be a 33 over there. The 33 over there would be the 41 over there. And the 41 over there would be a 24 over there. That's one other set of frequencies in these 4 cells that would also add up to the same marginals and is different from the one that we have. Okay, now let's see. The probability of having this one, 45, 20, 29, 4, from the whole set of cell counts that we could have had there that all add up to these same marginals, the probability of that one, having exactly that one, is this. 65 over 45 times 33 over 29 divided by 98 over 74. In principle, a rather basic probabilistic calculation, but even, if you're willing to go past that, perhaps you don't even know exactly how this is calculated, you can see coming, if you know what this means, that these numbers will become very, very large and nasty to calculate. You have things like 98 faculteit. Not sure what that means in English. You know?
Factorial.
Sorry? Factorial, sure, thanks. So 98 factorial, which is a huge number. You don't need the 98 factorial completely, especially if you divide it by 74 here, but still, this is nasty to do the actual calculations on. And what we're going to do is simply map out all the different numbers that you could have there, and then look at those and try to figure out how weird the one is that we actually have. That's what Fisher's exact is doing, and it's not making any kind of distributional assumptions. So no normal distribution, no chi-squared, no nothing. And that's also what is stronger about it. Okay, so let's see. Well, we simply start from the beginning. This is one that I already started with. 0 in that bottom right cell. Then 33, 41, and 42 is in fact the only possibility that you have to end up with these same margins. Okay, next number. A 1 there. Okay, so we have 32, 42, 23. And that's pretty much it. Next one. 2, 31, 30, 43, 23, and so on, all the way up to 24. In this case, it's relatively soon that we're done. We have only 24 here, and this is because the table is so small, 2 by 2, and there are not so many possibilities. But imagine that the table would be 10 by 10. We start from the, from the bottom right, start with a 0. Okay, then we still have a huge matrix that could be filled in many different kinds of ways. And enumerating all these different possibilities to end up at these marginals is a bucket load of work. Okay, I see many people pointing out to each other exactly what the issue is. If it's not clear, just ask. He explained it well? Okay. Any questions here? So we're trying to simply count out what the different ways are to end at these marginals. And for 2 by 2 tables, it's not so bad. We have 25, 1 through 24, and the 0. Okay, now, next part would be, for all of these, determine which of these 25 that we have over there are further away from H0 than the actual data. H0 is this, 48.8, 25.2, 15.8, and 8.2, based on these marginals over there. So this is what I expect if there is exactly no relation between the two. And now from that set of 25, I'm trying to figure out which of these are cases that are further away from H0. And I'm looking at the 5% of these cases that are furthest away from H0. Basically, in the same way as I did it with the coin flips, I'm looking at, there was way easier, 500 is expected. I'm looking at where the numbers are, in all likelihood over there and over there, that are furthest away from H0. It's the same thing over here. This is what we're expecting. I'm looking at cases here where we have to determine which of these are furthest away. In this case, again, because it's 2 by 2, this is relatively easy. But picture yourself doing this for a 10 by 10 table, where you first count out a gazillion ways to get these same marginals, and then have to plow through, okay, which are the 5% here that are the most extreme away from H0. Stata does it for you, so that's the good news. But as soon as you have this, as soon as you know, okay, from this set of 25, I have these 5%, these are the ones who are furthest away, then you check if your actual data is one of them. Check how likely it is that the case that you have would indeed be in that 5%. So that's in principle the same thing as with the coin flips, only wildly more complicated. First because of all the enumeration stuff, and second because of all the probabilities that you need to calculate with the different factorials in it. So here goes. We have these 5%. We calculate all these probabilities. How likely is it, if you distribute these numbers across the different cells, that you get the one with the 0 in the bottom right, the one with the 1 in the bottom right, and so on. You calculate out all these probabilities, and now in the end you check, let's say, how bad it is in terms of the data that you had. So the one that you actually had in your data, the one over there, is that in the edge, in the 5% of cases where you would think that H0 is the furthest away. And the answer here is in the chi-square. It was yes, and we will see if this is also the case in a Fisher's exact. Do we have this example here? Oh, this is not the slide I want to show. I want to show this one. So here we see the same thing. Only difference there is I add the exact command, telling Stata, okay, do the whole enumeration stuff. You will see, if you have a very big table, that Stata is enumerating, and that will take a long time, not for a 2 by 2 table, but for larger tables it will. And in this case, you get a different number over there. Well, it's only slightly different. It's 0.049. So with the chi-squared, you see that it is below 0.05, and in this case, with the Fisher exact, you also see that it's below 0.05. Conclusion, H0 rejected either way. What you will typically see is that the Fisher's exact is a bit more conservative, so in the sense that if you calculate both chi-squared and exact, then you'll get most of the time a larger number there for Fisher's exact. Yes? You had the, yeah, what was it?
So Fisher is actually the same as chi-squared, but only it lets out like there's a 5% which creates the most.
No, so chi-squared and Fisher's exact test the same thing, namely if the rows and the columns of the table are independent, but they do it in slightly different ways. Chi-squared assumes that normal distribution, and that will lead to a chi-squared distribution, but that assumption is sometimes not good enough, so to speak. So if we don't have that assumption, then we have to do it through that Fisher's exact method, and that will always work, which is obviously suggesting the question, okay, if that one always works, why don't we just do that one all the time? And the answer is quite straightforward. As soon as we have tables that are bigger than this one, and data sets that are even slightly larger, then Stata won't be able to solve it in a finite amount of time. And anticipating this, Stata will simply start enumerating and at some point say, okay, this is not going to work. Do something else. So that is the reason why you need to know them both. So there are cases where you can see chi-square is not good enough, and Fisher's exact is not giving me an answer. So you might be sort of stuck. The good thing is, no distributional assumptions whatsoever, so that whole stuff about normality and chi-square, none of that we need. Well, not necessarily not enough. What we do is we stick to the standard rule of thumb. If we look at the cell counts and we see that they are all 5 or higher, usually we don't bother with that. That is the standard rule. Okay, so back to what it is that you need to be able to do in Stata, because that is relatively straightforward. Only two commands. You create the crosstab, starts with that. You look at the cell counts, and you check if they're all bigger than 5. If not, you can try Fisher's exact. With Fisher's exact, it might happen that it doesn't give you an answer because the data is too large. Might happen quite easily for cases of many variables. So something else might be if you find that there is a column or a row in there that hardly has cases at all, as we have. We had in fact 3 columns where nothing was in there, or close to nothing. You might consider, okay, let's forget about these cases, and let's simply do the comparison on all the columns where I do have cases. There are nevertheless examples where you're somewhere in between. You have a large 10 by 10 table. There are here and there a couple of cell counts that are 0 or 1, but not whole columns that are 0 or 1. Then you simply have to decide what works best here. Either trying to run Fisher's exact, but that will in all likelihood cause that the whole thing won't converge in finite time, or run chi-squared and don't bother too much about a single cell count that is below 5. That's basically the only option you have left. Okay, that is all chi-square stuff. Any good? Yes?
Just earlier you used the exact y and then row chi-square.
Yeah. I added a row option behind the tab if I want to add percentages in the rows that add up to 100%. That might be useful to see, so let's see if here I don't have it. Let's see, for instance, here I can see in there's that one. Here I added the row as well, and here you see 4.7, 62.5, and so on. This row here adds up to 100%, so that it gets easier to see if there are differences percentage-wise in the distribution for males or females. That's the only reason. And given that there is an option to type row, you could correctly assume that there is also an option to type column, C-O-L. Then you get percentages column-wise instead of row-wise. Okay, more questions about this part? This is the easy one. The rest is seriously more complicated. Oh well, still not so complicated that it's too difficult, but this is the easy one. What else do we have? Yeah. Final thing about these chi-square grades. If, in the end, we find that there is a difference, a dependence between the rows and the columns. So in this case, when we had boys and girls and how they arrive at QE, and let's suppose that we reject H0. So apparently there is a relation between being male or female and how you arrive on campus. Then the likely question would be, how big is the effect here? How big is the difference? Smaller effects are simply less interesting. Huge effects would be nice to know. And to quantify this, there is one way to do it that has become standard. It's called Kramer's V, or sometimes also Kramer's Phi, depends a little bit on which book you read. And the formula for the size of the effect looks like this. Now let's have a look at what's in there to try and understand why it's as it is. Because the first idea, and that's relatively obvious, is that that chi-squared value, that 7.27 that we had in the example, that's not so weird that that is in there. The bigger the number is, the bigger the difference is. So that it is the case that if chi-squared gets bigger, then the effect size gets bigger, that is something you could expect. However, what you should take into account, obviously, is that if you have a really big table where you square lots and lots of differences, then it's also obvious that you get a bigger number. So you should somehow compensate for how many of these different square differences you have added up. And you do that by that k minus 1 over here. K is in fact the smaller dimension of row and column. So if you have a 2 by 5 table, smallest of that is 2, and then k minus 1 would be 1. And this is compensating for the fact that, you know, a long list of square differences is likely to get a big number. So this is why we divide by something related to k. And the other thing is, well, n, that is the number of observations that you have. There you can also imagine that this makes a difference, because if you have a very, very large n, that will mean that the marginals, so the numbers on the edges of the table, are also relatively large. And that will mean that the cell counts themselves are also relatively large. And if I have relatively large numbers in the cells, it's easier to miss by a big margin. And if that's the case, that should somehow compensate for the fact that, yeah, if I have a lot of observations and a lot of room to miss, yeah, then it's not so weird that I do. And to compensate for that, we also divide by the number of observations. And the standard rule is then also to take the square root of that number, but, you know, that's just a convenience. And then, of course, you need to know something about what is then a big effect size. And again, I think in different statistics books you'll find different suggestions here. But by and large, anything bigger than 0.5 would be deemed a big effect. Anything below would be a small effect, and it depends a little bit on the book what you call big and small. In fact, I don't say it completely correct. This is what is standard in all tables except 2x2 tables, because in 2x2 tables there's a different measure of effect size, and actually then it's this one. Calculated slightly differently. You need not bother with that. Stata will take care. Close up your laptop. You smash that close. Okay, something that I should remind you of, that I just realized. Here, when we looked at what the effect size actually is, we went through the whole idea about this thing over there, giving you a number in the end, and I didn't mention that. It runs between 0 and 1, where 0 would be no effect, and 1 would be a very large effect. That is very often the way in which effect sizes are measured. The minimum is nothing, and the maximum is 1. However, I did mention, and there it starts to become a little bit weird, that for smaller tables, 2x2, the definition is slightly different, but it's actually more than slightly different, because as you see in the small print right over there, where originally here the print was G is running between 0 and 1. For 2x2 tables, there's a different definition, and it's now running between -1 and +1. It can become smaller than 0, which is sort of weird. You still have -1 is not very good, and +1 is very good, but the whole scale of the thing, it changes if you look at 2x2 versus many by many tables. This is something to take into account if you happen to encounter a 2x2 table. Okay, one more example from our data. This is something that we saw in the actual survey. Yeah. I must check, but I think yes. I think still the threshold is 0.5, but I must check myself as well. Okay, this was a question in your survey. Excuse me, are you done? Yo! You're done? Thank you. 2 conditions, and you were in 1, not more. First condition, program A, is of the following kind, in the scenario that you all had. Scenario is, imagine that the US is preparing for an outbreak of an unusual Asian disease. It is expected to kill 600 people, and 2 alternative programs have been proposed. Assume the exact scientific estimate of the consequences of the program are as follows. And then you get either condition 1 or condition 2. Condition 1 is such that program A says 200 people will be saved, and program B would be that there is a 1/3 probability that 600 people will be saved, and a 2/3 probability that no one will be saved. question is, okay, what do you want, A or B? And condition 2 is program A is 400 people will die, or program B is there is a 1/3 probability that nobody will die, and a 2/3 probability that all will die. Okay, the first thing to note is that in terms of the numbers, there is no difference between condition 1 and condition 2. Okay, so program A here, 200 will be saved. This is the same as saying that 400 people will die. Only one has the emphasis on living, and the other one has the emphasis on dying. And the same goes for B in both cases. So you shouldn't expect any difference in terms of preference for A or B. That depends on the condition. So if I ask this to you or that to you, it shouldn't matter. Now, this is a very famous example by Tversky and Cameron from 1981, where very often we know that we do find differences here. So apparently it does make a difference how you present these two programs in terms of living or in terms of dying. And we'll see if this is the same in our data. So first, here you see a tab of the variable itself, age and disease, and this was done at random. So in the end, it turned out that 92 of you were in the live frame, so that means where we say 200 people will be saved, that's condition 1, or in the kill frame, that is number 1 here, 74 of you were in there. And then here, the respondent chose a certain option. Certain would be A there or A there. Here in, let's see, 99 of the 166 cases. So that is simply the tab of the separate variables. And now let's see if there is a dependence between these two. You can do this like this. A tab age and disease, and X age and disease, all exact columns, column percentages, and V for the effect size, just giving me all the output that I can work with. Well, let's first look at the tabulation here. If we have numbers in there that are below 5, we don't. So we're good to go with the chi-square test, which is nice. What is less nice is that, well, first, that's still okay. If you sum up these square differences, then you get a number that's 3.8, okay? And that turns out to be an alpha value of 0.051, so slightly above 0.05. So we're still supporting H0 and not reject H0, but it's really, really close. Here we see the parameters V, in this case, in fact, smaller than 0. In the 2 by 2 table, this can happen, and here it does happen. And we also see the Fisher's exact test, and again we see what we saw before, that the number that you now see over there, the 0.058, is slightly larger than the 0.051 that we had. So again, we see, well, we barely support H0 here. It was close, but apparently we have to conclude here H0 is supported. So the difference that we normally find here, in our case, we didn't find, actually. By the way, here you can, you know, if the question would be at an exam or where else, is this an experiment or a survey? This is obviously typically an experiment, because this thing is something that I measure. If you chose the upper option or the A option or the B option, but this one is something that was under my control as the experimenter. So this is an experiment. I created that here. Yeah.
So what's the one-sided Fisher exact?
Yeah. This is the part where I sort of hesitate if I want to go into these kind of differences. For each and every test, you can have one-sided and two-sided tests. And the difference is as follows. The easiest is to consider the coin flipping example. Once again, so we have 1,000 throws of the coin, and 500 is, let's say, expected. And now we think about what is weird, and weird could be all the way over there or all the way over there. And as long as we do not have any particular preference, then the alpha equal to 5% pertains to 2.5% over there, because that's weird, and 2.5% way over there, because that's equally weird. If for some reason we have a clear expectation of where we think the coin is weird, in which direction I think the probability of heads is higher, then you could argue, okay, there is not likely at all, and I put all the 5% on that side. Now we get a one-sided test. And the same thing goes here for the Fisher exact. You could test, standard would be two-sided. You do not really know if there is a difference, could be here, could be there. you put 2.5% on each side, or if you have a specific idea about in which direction the difference would be, and in this case I would have no clue, but if that would be the case, then you get a one-sided Fisher's exact test with all the probability mass on one side. And typically what you then get, always, is that the number that you end up with here, 0.037, is smaller than the number that you have for a two-sided. So in this case, if you would have a strong argument, I don't, but if you would, for a directional difference, where you could argue we could run a one-sided test here, then H0 would actually be rejected. But very, very often we stick to two-sided tests, normally because we don't have an idea up front about where the difference would be. Yeah? Oh, I don't know if I really had an idea here. Let's see. Yeah, I do have an idea. I choose the columns here because, well, here in the columns you see what people chose. And I'm looking at, is there a difference in terms of percentages between condition 1 and condition 2? And here I can see, this is the condition. 66% chose 1 in the one condition, and 51% chose 1 in the second condition. So if I look at these, this already gives me an idea of whether or not there will be a difference. If I would have found 66 twice, then you could stop looking altogether. There is no difference. So this gives a bit of a feeling for how large the difference actually is. And in this case, using the row, wouldn't have made much sense. You would have these percentages added up to 100 like this, but that's not a comparison that you want to make here. So this is why I had the column. Other questions about this? Okay, so this was the conclusion. Here, H0 supported, albeit barely. Yeah. No, I didn't say it was always between 0 and 1. I said it was always between 0 and 1 for all non-2x2 tables. And it could be between -1 and +1 for 2x2 tables, and that's happening here. No. First of all, in this case, I added the Kramer's V simply because I wanted to show that state will give it to you. But here, if you actually do not reject H0, we have, what we're saying is there is no effect large enough to bother with. So in this case, we didn't look at this at all. And if you would, then there is no negative effect here. The lower value is -1. It's weird. Of course. So this goes against Kahneman and Tversky's stuff. Apparently there is not big enough a difference in this case to conclude that there is an actual difference. Okay, on to another variable in our data that's slightly different. Just to get our minds off the chi-squareds, and that's this one. The variable in the data is called hit target. The idea for this variable was, there was a little bit of text above the variable where it said, okay, do the following, raise your arm like this, look at the thing over there. Now close your eyes and pinpoint the target that you have on the screen. And the assumption was, of course, that what you didn't do is increase that target in such a way that your whole screen would now become the 10 over there, but you just stick to that thing. Here you see a distribution of how many times people actually have hit the target. And the question is, of course, what are we measuring here? And one idea could be, what we're measuring here is actually something like hand-eye coordination or something. And I'm actually aiming for something else. What else could it be that we're measuring here? Yes. So what we're measuring here, much more, I think, than hand-eye coordination or what have you, is the extent to which people are telling the truth when they're doing this, or whether they have done it at all. First of all, if you actually do this, and you have, let's say, a decent-sized computer screen, not something that is a phone, then in all likelihood you won't hit many, perhaps one by accident, but this is not very easy. You do it exactly according to scenario, hand in the air, eyes closed, and then you poke. Probability that you end up in that target right in the middle is really, really small. So that would mean that these people over here, especially the 4s and the 5s, I think you're lying through your teeth. Okay, so this is certainly not what you managed to do. Now, why do we want this? These kind of things we typically want because all this is survey data on the internet, and we know that people are reluctant to pay attention to it. So typically what I would like to have is stuff of the following kind in an internet survey. I want to be able to control, at least somehow, who is messing up my data. And one way to do it is by a question like this, where it's not so obvious for most people at least, what the question actually is for, and some people do it, and are honest about that they do not hit the target. Great, I want those. And some people just say, 5 or 4, or do it and then lie that they scored 4 or 5. And I'm less likely to like their data, because they're somehow changing the truth somewhat, and perhaps they're doing it for other questions. So the question here is, if this is one way to do it, come up with a couple of other ideas to make sure that you can at least check who is okay from your response and who isn't. What do we do then? Any other suggestions? Yeah.
Ask a couple of questions, but in reverse, like in a negative way.
Okay, can you give an example of?
Do you like this class? And then later on ask, do you not like this class?
Yeah, so it's kind of a control question in the sense that you ask it twice and slightly different. This is a standard way of doing it. One big risk of doing it like this. Typically, the kind of question that people use is not something like that, but for instance, way at the beginning you ask how old are you, and then you're supposed to answer in years. And way at the end of the survey I ask what is your birth year. And if there's a big difference between the two, then apparently something weird is going on. Most likely that you're lying. And the disadvantage of this is, as soon as people find out that this is actually happening, they start getting annoyed. And if they get annoyed, they're more likely to stop. So that's the risk of these kind of questions. You don't want to have too many, or too many of them are totally obvious, because this is not very, people don't like it. Other ways to do it, yeah. Sure, time measurement, that's another standard one. Although we did some extensive testing in this area, and it doesn't work so well. I can show you the same thing here on our own data. We had, when I looked at the time that people took for the whole survey, we get a couple who had 1.5 minutes or so. So I'm looking at these 1.5 minutes, okay, that can't be right. I look at the data, and these are all cases where people have, for some reason, participated twice. Once they started and then stopped, and then some other time they restarted and completed the whole survey. So I simply got rid of the ones where they started but didn't complete. Fine. Then we get the lowest values that are, let's say, borderline. 6 minutes, 7 minutes. I hardly believe it, but if you're really, really fast, perhaps it's possible. So there is a threshold. At some point, I'm going to say, okay, 2 minutes. No, I'm not going to believe that. But it's not so obvious where I should start believing you. And it's even worse at the other end. Because if it takes really, really long, if you look at the time's in there, you will see that there are a couple in there that took 3 hours or so. And that can only mean that they left it open for a long while, and then went into something else, and then in the end completed. In principle, if you were paying attention as soon as you were filling out these questions, I don't mind so much that it took a long time. So I'm sort of leaning towards leaving them in. So all the ones with a very long time, that doesn't help me much because, what can I do? And with a short time, I have to check, okay, where am I putting my foot on the brake here, where I believe no longer that 5 minutes is good enough. You can be more detailed, of course, keeping track of times per page. I didn't do that in this case. Then you could also see that, if you're only there for 1/10 of a second, apparently you haven't done so much. But, it's possible, and one extra way to do it. And I think one of the main strategies here is to try and come up with a couple ways of measuring this. For instance, putting, let's say, a little red flag near somebody for every weird thing that he or she does. So, you say you score 5 times on that hit target thing, okay, big flag near you. It took you 3.5 3.5 minutes to complete the whole thing, another big flag near you. If in the end you have a low list of these flags, I throw you out. That's the standard idea. What are ways to try to figure out if people are messing up your data?
Look at patterns, how they respond to fail.
Yeah, on the dreaded matrix questions, for the following statements, mention to what extent do you agree with, and then you get a list of 20 where you somehow need to go through it. Very often it's not even possible to go to the next page. And what people could do is just click, 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 click. So what you could do is simply check for each and every person in your data, is it the case that they have the same answer for this battery of questions on each of these items? Of course, this is not completely foolproof. If you accidentally or deliberately clicked one to the left and one to the right, or do it at random, then I don't find you back. What I do tend to do is try to find if you have a zigzag pattern, so the ones who do this, try to find those. And then again, sets a couple of flags near some people, and some are still good to go. And if you have quite a few of these questions, you end up with a larger set of potential flags. The ones with more flags are the ones that you are more likely to leave out. What other ways do you check? There's more. Yep.
Ask them to type over a specific question.
Yes, that's another one that was actually in the questionnaire. Ask them to type something random, no, not to type something random, but type something specific, but random to the survey. Here the question was type, I think, TUE 2016 or something. This is simply to check if you read the questions. If you know I have to fill out the question somewhere, and this is being checked when people are willing to type anything, just to go through the whole survey. If you don't type TUE 2016, you apparently weren't reading any kind of questions. Again, another big red flag near you. Finally, one other thing that we can do here, which would be what? No. Sorry? Yeah, that's also one that we saw in the actual survey way in the end. If you have been lying all the time, I actually prefer that you simply admit it. Then I have data, and I know, okay, I shouldn't pay too much attention to it. And that's still to be preferred to where you say, okay, I was totally honest, but actually lie. So very often, people do not mind so much, at least admitting in the end that they weren't paying attention very much. And if I know that, then I'm good to go as well. One other thing that I want to mention is something that the people tend to have different kinds of feelings about, and that is if you have to force people to actually answer questions. Obviously, that has the advantage that if you then get data back, then everything has to be filled out. You have lots and lots of data. But the risk is, of course, that people have simply clicked something in there because you asked and sort of forced them to click something, and then you don't know if the answers are correct. So normally, my preference would be not to force too many answers, because the risk is that you'll get it. And if you get it and it's simply not what you're supposed to be measuring, then you have the wrong data. So just these big matrix questions, leave it optional to fill them out, and simply check in the end who was, let's say, too lazy to go through the whole item vector set. Okay. One other thing before we go to the next command, and that is, instead of the tab command, there is a command that is closely related to it, it's slightly different. Actually, tab is an abbreviation of tabulate, and there is another command inside there is called table. It looks like this. Table female terminal TUE, so that's very close to the actual tab that we had. The only thing is, what I can now ask is, in the different cells, give me something else than just the frequency that I'm expected that I have in the different cells. For instance, here I asked for, well, content n is for me, and age is a variable in my data. So this is saying, okay, show me a crosstab of these two variables. In every cell, give me the mean of age. Here we see for female, no, this is males for zeros. Here the average age is 22.3 for those who came on foot. And for quite a few different examples, it's useful to be able to generate a crosstab like this through the table. We can do more here. And for me, it's just one example. There are different ways to get different outputs here, standard deviation, frequency, any kind of different things you might want to add. Okay, wrapping up. For this part, using chi-square and features exact, you can compare two variables where each of the variables is categorical with two or more categories. That'll work. Test follows the same logic that all tests follow. If H0 is true, where H0 is rows and columns are independent, how likely is it then that I get the data that I have, or data further away from H0 still? Kramer's V gives then an idea about the effect sign. Will you get rid of the phone, please? Or do it outside? Thank you. That wraps up the two variables, both categorical part. Any questions about this? Otherwise, I'll assume that this is common knowledge as of today. Yeah.
How often does it happen that the two variables are, if one of the variables with more values than two? Like one with 5 and one with 6, instead of one with 2 and one with 5 and 6.
Yeah, depends totally, of course, on the survey that you create. Normally, you're the one creating the survey. So you can try to make sure that you have quite a few or not so many of these kinds of variables. It depends on the topic as well. Let's say a survey about, let's say, how satisfied you are with your living conditions. And one of the questions would be, you live in what? A house? An apartment? And you can come up with a couple of other ones that are all completely different. And you could ask things about, hobbies, who knows what, and they're also in order in them. And then you could easily have quite large mix. So it depends totally on what the actual topic is, and of course on the questions that you ask for that topic. Other questions about this? Okay, that's this one. Up next, t-tests and more. Yeah, quite a bit more actually. Because all the stuff that you already saw in the one before, where you have to check are all the cell counts, at least 5, that was still relatively easy to do. There was only one thing to check. And then if you found that it didn't work out, there was only one thing to do. Well, that number is going up for this example. And the example is about comparing two kinds of variables where one of them is categorical with two categories and the other one is interval. And these are the commands that you need in Stata, or at least part of the commands that you need in Stata that we'll go through to figure out if there are relations between these two variables. Examples. All of these are about comparing two groups across an interval variable. For instance, do girls score higher grades than boys? We have that in our data. We have boy-girl, and we also have the average grade, so that is something we could test. Then something that we don't have, do people over 65 have a lower heart rate than people younger than 55, so we have above and below 65, categorical, two categories, and something that is interval scaled, heart rate. Or, as we've seen before, do you have a higher heart rate when you relive an angry memory when compared to when you measure your standard heart rate? That's what Daniel Lakens did in the Introduction to Psychology course. So you have two conditions there, the categorical variable, two conditions. One is the standard condition, you don't relive anything, or you relive an angry memory, and the comparison is between the heart rates in these two conditions. How do we do this? Again, first, what you need to be, run through sort of as a recipe in Stata. You see here already at least a little bit that the recipe itself is a little bit longer than it used to be for the chi-square exact. It starts with that you have to test for normality. What we'll find out is that the t-test that only will work if in the two groups that we compare, that interval variable has a normal distribution already. For that you can use many commands, but we will use two. One is called SWILK for Shapiro and Wilks, and one is called SK test, where S is for skewness and K is for kurtosis. So this is skewness and kurtosis test. If you've tested that, that you typically do first. Then you run a t-test through this command. T-test on y, where y is the interval variable, comma by x, where x is the variable with two categories, and you add an additional option there that's labeled unequal. More about why that's there in a minute. If it doesn't work out, so you check for normality in both of these groups, then you could try to make sure that the variable that you had, that y, that you transform it in some way. Take the square root of y, or the log of y, or something else of y, in such a way that it now is a normal distribution, or at least close enough to a normal distribution. If that works, great. Then we now do not run the t-test on y, but the t-test on the transformed y. And we're back to 1 again. But it could, of course, be that you cannot find any kind of transformation that will work here. No transformation will turn that distribution into something that resembles a normal distribution, and then you have to do something else. And that is a rank sum and or a median test. So, loosely speaking, where in the other example, this was the Fisher's exact. If all the distributional stuff doesn't work, then there is a last resort, and it's this one. Here is something similar here. And then, of course, we get the following kinds of issues, something that might pop up every once in a while in all kinds of statistical testing. You do two tests for the same thing, and what do you do if the different tests deliver different answers to that same question? Well, here it's pretty clear what to do. These two test for normality, and normality has to hold irrespective of how you test. So if either one of these doesn't work out, rejects normality, okay, forget it. Then you have to do something about it. Here it's slightly different. If you are not able for some reason to run the t-test, and you have to resort to either the rank sum test or the median test, it might be that the median test, let's say, supports H0 and that the rank sum test rejects H0. Yeah, then the first thing to do is read again what these tests actually do, and in this case I slightly favor the rank sum test. I'll explain as soon as we get there why that is. But normally what you do is simply stand like this and hope that they deliver the same answer. That will be more easy. Okay, so this is the recipe, and we're on our way to get that done. To get this done, I need to do something in the data to come up with an actual variable that follows these guidelines, an interval y and a categorical x. And this is the one that I'll use. We measured happiness in the data through items like this. This is one of these item batteries. I don't feel particularly pleased with the way I am. I feel that life is rewarding. I have warm feelings towards almost everyone. And there are quite a few of these, in fact 14, and these were measured on a 1 to 6 point scale, where 6 was strongly agree and 1 was strongly disagree. Then, more on that in another lecture. One way to calculate a sort of sum score for all of these is using the alpha command. What the alpha command does is simply averaging out your scores here on these separate items, taking into account the wording of the different items. So here you see, for instance, say I find most things amusing, which is, I guess, related to happiness in a positive way, or I do not think that the world is a good place, that is a negative item. And what that alpha command does, and you can see it already a little bit through the pluses and minuses over there, is making sure that these are all turned in the same direction, and then averaged out. All this, how we interpret that, we'll talk about that later, but this gives you your average score on these 14 items. That's the y variable that I'm going to use. And the categorical variable that I'm going to use is another one that was experimental. There were two conditions in the survey, at random delivered. So right before you answered these items about happiness, you either saw the picture on top there, the guy sitting against the wall, not looking very happy, and or the baby that you have over there. And the idea would be, or the idea at least that we can test, is it the case that you score higher on these happiness variables right after you've seen a picture of a, well, let's say of a happy baby, not sure if that's happiness, but of a funny baby, basically. And in this case, what we see is that, so we need not even go through the testing in this example. We will just to go through the motions. But here you see the means for the different pictures. In the top left, you see the depressed guy, and in the top right, you see the baby. Well, we're trying to test here, do people score higher on happiness if they saw the baby? Now, if I look at the two groups here, I see that the median over there is 1.27. The median over there is 1.18, which is lower. So this is certainly not going to deliver that people are happier when they have just seen the happy baby. At best, we might find that if you see the depressed guy, then you score higher afterwards. The argument could be, for instance, you see the depressed guy sitting over there, and then you think, see him being depressed, it's not so bad for me. That's a good thing. Okay, how can you get these means? Because the mean this picture over there, this is an actual graph, of course. The graph doesn't give you the mean itself in the picture. You have to add a scalar for that. One thing I'd like to emphasize here, and you'll see that more often than not, is that for many of these things there are different ways in Stata to make sure that you get the correct answer. For instance, here, if I want to compare these means, we see three different ways of getting that mean from Stata. And there are, in fact, more than this. One is through the summarize command. Summarize the happy variable if the happy baby equals to 0, and summarize the happy baby variable if the happy baby is equal to 1. And then you get here the 1.27 and 1.93. That'll work. There are two other ones that I showed here. One is the buys happy baby, show me a summary of happy. That will do the same thing, but in slightly different ways. And that table command that we looked at before will also work. Of course, if you encounter these kind of things in the wiki pages, there is no need to change something that's there by another command that does exactly the same thing. It's nice to know that you can do it in different kinds of ways, and as long as you get the right number, well, great. Okay, let's see. This is what we would like to do immediately. So this is the t-test command that we can run if all the assumptions work out. That would be nice. T-test. Happy right there, buy happy baby, and we add the unequal option right there. That gives us quite a bit of output, including these two means that we were calculating on the previous slide, 1.27 over there, 1.19 over there, and a lot of other stuff, all of which we will go through in some more detail. But it also gets, and that's the important thing I want to emphasize here, is that probability statement at the end, where in this case we would aim for that one in the middle. Here you see, if we are aiming for a value here below 0.05, well, we don't have it. So in this case, what we get is H0 is certainly not rejected. Okay, we're not supposed to go into that just yet. And we need a little bit of extra stuff before we can actually go there. The first stuff that we need is a little bit of statistics behind us. First, something that you must have seen before, that is the definition of variance. Variance, we've mentioned this a couple of times already, is how hard you differ from the mean across all cases. And you calculate it like this. This is the mean. You look for each and every case, how far is it away from the mean. You square that number and you divide it by how many cases you have. It's called the variance. The standard deviation is exactly the same thing, only the square root of this. And it measures something of, for instance, in a normal distribution, how wide that distribution actually is. Nothing new. Now, for many of the things that we are about to calculate, you need an estimate of that variance. You need an estimate of the width of the actual distribution in the population. But the trouble is, we don't have data from the real population. We only have the sample. And there, where you see the Greek letters for the population, you'll see estimated variances denoted by small s. That's something to take into account. As soon as you see Greek letters in statistics text, these letters normally refer to stuff that relates to the population. When you see non-Greek letters, such as this S, normally also the letter that belongs to the letter in Greek over there, this is the estimated variance as we get it from the sample. So one thing we could do is, okay, I have no clue about the variance in the actual population, but I can calculate the variance in my sample and use that as an estimate. In fact, that's not exactly how it is done. That would be this one over there. And Actually, there is not an n in the denominator, but an n minus 1. But okay, let's forget about this. Okay, now let's see. How could we come up with an idea about whether two groups differ on an interval scaled variable? Well, this is what it sort of looks like. Here, these two humps over there are supposed to represent two normally distributed variables. The green one is for the one group and the blue one is for the other group. Now it's totally obvious if the green one and the blue one would totally coincide, then there certainly is no difference between the groups. Apparently the distribution is totally overlapping, so there is no difference, certainly not between the means of the groups. If they are totally separate, one is all the way over there and one is all the way over there, then we know, yeah, there is a difference between these two distributions. So if you're trying to figure out if there is a difference between the means of these two distributions, one thing that should be factored in there is the difference in the means of these two separate ones. So this x mean t minus x mean c, that is this value over there, the midpoint of the green one, and that is the midpoint of the blue one. If these two humps are far apart, this is suggestive of a difference. If these two humps are very close, this is suggestive of no difference. So that is something that should factor in the statistic that we're going to use. But it's only one part, because the other part is, well, we somehow should take into account how wide these humps are. If these are really, really small, so there is a really small peak, then even if these two peaks are relatively close, if these peaks themselves are really small, then there is likely to be a difference. On the other hand, if these humps are really wide, so there is a difference here and there, this is where the midpoints are, but both of these humps are so wide that they are stretching all the way to the right and all the way to the left, then also it's not easy to conclude that there is an actual difference. So this is suggesting already that we need at least two parts here to try to figure out if there is a reasonable difference that we can discern between these two normal distributions. And it should include, first, the difference between the midpoints, and that is the difference between the means, and second, it should include both of these widths of these humps. And that you can calculate, this is why I needed this part. The variance is a measure for how wide that thing is, that we will need, and where the midpoint of these two things is. Okay, this is the part where we're sort of gradually moving away from where we still bother about what the exact statistics looks like, and start to believe what others suggest to us. What we had before, the coin flips, you could do that. That was binomial probabilities. If you do the calculations, well, we can do it. The chi-squared, you could vaguely feel perhaps that, squared normal distributions, that in the end gives us also a distribution that might work, where a bigger number represents more likely that it is a weird outcome, so to speak. Here we have something else. Here somebody came up with this thing, labeled T. And from that T, actually the only two things that I want to emphasize here is first, that the mean of x and the mean of y is in there. So indeed, to try to figure out what this number is, and if this number should be representative for whether or not there is a difference between these two normal distributions, indeed, the two means and the difference of these two means is in there, so things further apart are more likely to be different. And something else that's in there is these S's, that is the width of the one distribution and the width of the other. There's also the number of cases in there, forget about that. The thing is, here we have somebody else who came up with a test statistic for us that follows the same logic. If this value here is high enough, it starts to be pretty unlikely that these two distributions are actually the same. If this value is really low, or close to zero, I should say actually, then it is relatively likely that these two are the same. And these t statistics sort of look like normal distribution. Not so much different, depends a little bit on how large n is. As n gets to infinity, the t distribution resembles the normal distribution closer and closer. Okay, so at this point we don't bother so much with, okay, how do we get this and how do we understand this? Somebody for us came up with a test statistic that we can use to evaluate if two normal distributions themselves are different from each other. Okay, there. Let's see if we understand this. This t-value increases as the difference between the groups is larger. I understand that. And the t-value decreases as the estimated width of the distribution is larger. This I also understand, because the wider that distribution is, the less likely that I can find a difference, or stated differently, the tighter that distribution is, the easier it is to find a difference with another distribution. Okay, so, main message, we came from there, point, and a distribution that we could think of ourselves, or at least simulate. Then we had tables, and we came up through some hand waving with a chi-square distribution. The chi-square distribution gives us a number that we can work with. And the third one, we compare two normally distributed variables, and somebody else now comes up with what's called a t-statistic for us to figure out whether or not two of these normal distributions are actually the same, all the same. And here you see that they're all the same. They have an H0, coin is fair, and then in the end, here we have a approximately normal distribution. All rows follow the marginal distribution. We have something that's called chi-square, or here the mean of the red one